I do want to spend some time talking about really ancient astronomy, pre-written astronomy, archaeoastronomy, which is a combination of archaeology, because you have to go to these ancient sites, dig through the dirt, figure out what's going on, where everything's located, and then infer the astronomy, and hence archaeoastronomy. There, as you all know, there are archaeological sites all around the Earth, thousands, tens of thousands of archaeological sites. You know, people have been around for a long time, they left stuff behind, so they're archaeological sites. A great many of them are also astronomical in nature, which is really kind of interesting. And it's actually more than you think. It's not like a rare one happens to have some astronomical properties. A lot of this research began in the British Isles, and that's where you'll see my knowledge base. I'm not an expert in this field, but I am kind of an expert at one site, and that's Stonehenge. We'll be talking about that today and into the next class. I'm going to tell you more about Stonehenge than you'll ever need to know, than you'll need to know in the homeworks. It's just going to be kind of a fun exploration that we'll do over the rest of this class and the beginning of the next class. So my knowledge base is kind of there. I know in the British Isles there are about 300 archaeological sites that have been identified as having astronomical properties. By astronomical properties, I mean you stand, and these sites can be really simple. They can be just two stones, where you stand at one stone, the other stone, let's say I'll do it right, the other stone would be over there, marking where the sun comes up on the first day of summer. So you stand over there, and if this, as we talk about, the sun rises at different parts of the horizon. On the equinoxes, it rises due east and goes over the southern sky. In summer, it rises north of east, and winter south of east. The most common archaeoastronomical alignment is summer solstice sunrise. You know, across Britain and across the Earth, we see this. We have one stone telling you where to stand, and the other one marks where it rises on the first day of summer, the northernmost rise point. It doesn't work any other day. It just works that day. If you stand at that one and look back, it marks winter solstice sunset. So with two stones, you can mark the beginning of summer, beginning of winter. And I'll ask you why do you think that is in a second, but let me get your question. Good question. The question is, how did they know what was the first day of summer and the first day of winter? Well, they probably tried it. They made some mound or stone telling you where to stand, and then before dawn, they see the sun rising, and they mark it with a post or make it more permanent later with the stone. Come back the next day and they say, oh, it's not marking the sun's location anymore. The sun's now rising a little bit farther north if you're approaching summer. And so they move the marker and then farther north, till eventually you get to the northernmost location. And then it stops there. And for a couple of days it holds its position, and then starts working its way back as you move into the next season, through summer towards fall. It stands still. Solstice means standstill. It's the standstill point. So in terms of horizon astronomy, noticing where the sun comes up, which everyone's getting up before sunrise, working the land, working with animals. You have some kind of horizon, mountains, markers, and you notice, oh yeah, it's coming up over that nook there between the two mountains. It's coming up over there, coming up over here. People knew where the sun rose in different seasons, and they would mark it. There's vast archaeoastronomical evidence that they, for thousands of sites around the world, they've marked the beginning of summer and the beginning of winter. And why do you think that would be important to them? Harvest. Now, across culture, we see this everywhere. They're making a basic calendar. And the reason you do that is if you plant your crops a few weeks too early or a few weeks too late, more people than usual die come winter. It's harsh. It was harsh living back then. It's not easy like we have it nowadays. So you had to plant at the right time, and they needed some way to know when the right time was. And so this is the easiest way to get a calendar without, your cell phone or your laptop syncing to the U.S. time standard. So these things appear everywhere, and they're quite simple. But some of them went above and beyond. And as I said, I'm a semi-expert on Stonehenge, and you'll see over the rest of this class and the next class, there's a tremendous amount of astronomy there. But again, you can achieve astronomy with just a few stones. So I'm not trying to say that Stonehenge, its primary purpose is astronomical. I'm saying that it's embedded in all the architecture. Everything they did. It's probably a religious site or a site of political importance. No one knows. There's no written record. But we do know in examining the architecture, we can prove statistically that it's very significant astronomically. So that's what I'm going to do next. I'm going to walk you through this program that I put together when I was an undergrad. I was actually trying to get out of work. It was a winter program. When I was an undergrad, you could go to Britain for 2 weeks. and most everything was paid for. It was a good deal. But it was part of a class, and you had to write a 20-page paper. And I was sick of writing 20-page papers, so I said, okay, I'm going to do mine on archaeoastronomy. I hear Stonehenge is astronomical. I'll just make a computer program and simulate Stonehenge and the sun and the moon, and we can see the astronomical properties. Well, here I am, like, I don't know how many years later, 15, no, almost, yeah, 14 years later, 15 years later, and it's still not done. So I should have just written a 20-page paper. But it's done enough that I can show it to you. Let me just change my screen resolution, since when I coded this, I didn't make it expandable. So this is an overhead view of Stonehenge. You might be familiar with Stonehenge, the big stone circle. Here the stone's going around, top view. This is just a blow-up of the central region, and these are stones out on the outskirts. And as you might already guess, these are the astronomically significant stones. Why they put these strange stones here, there, in this weird configuration? You'll see they're all marking astronomical alignments. In the center, it's more geometrical patterns. You'll see that there's astronomy there as well. It works real simple. Pick where you want to stand, pick where you want to look, simulate, and there you are, 3 dimensions. Now this is before you had fancy graphics engines, so don't expect shadows or the grass waving in the wind or anything like that. You had to build them from scratch back then, and this is the best I could do. I'll show you another one close up. We'll go in here. If I hit it just right, we can see the sun in this view. Oh, cool. I've never noticed that before. You got the sun and the moon over here. So if you want to check on the astronomical properties, and most of these sites are solar and sometimes lunar, you got to build the sun and the moon in there. And that first seems easy, but boy, it's difficult to actually make it work right. I started out just by putting them on circles. The sun going around once a year, the moon going around once a month, but that didn't work. I went looking for the alignments and they just weren't there. And then I realized, oh yeah, they're not circular orbits. They're elliptical orbits, so I programmed in ellipses, and then still the alignments, because a lot of them have been figured out through time, and the ones that were supposed to be there just weren't there. And I realized it's a little bit more complicated than that. You have not just the sun tugging on the Earth and the Earth tugging on the moon, you also have the sun tugging on the moon, which has a back tug on the Earth, which has a back reaction on the sun. It's a 3-body system. 2-body systems are very simple. Kepler figured out how to do it. It's perfect ellipses. Newton explained it in terms of gravity. But 3-body systems are pretty tricky. They cause all sorts of strange non-elliptical behavior in their motions depending upon the relative locations at any given time. And it's not a completely solved problem. It's one of these things you can look it up in a book and it has terms and terms and terms, and you keep adding terms. The equation for the moon is like 100 pages long or something. And it's still an approximation, but if you add enough terms, it's good enough for this kind of thing. And so I typed all those equations in there. And if you get it like one sign wrong, the moon starts moving in the opposite direction. So you got to be careful. But I got it all in there just right. And you can see every now and then the hourglass pops up. It's actually recalculating the position of the moon and the sun, and they're moving across the sky as we're talking. And you got the phase of the moon in there correct as well. So I got that in, and I went looking for the alignments, and they still weren't there. And I had to think about this for a while. But the tilt of the Earth, we know the Earth is tipped 23.5 degrees. The Earth is like a top, as we talked about, that rotates on its axis, and the top precesses. But something else about tops we didn't talk about, but if you look at a top really carefully as it's precessing, it wobbles just a little bit as it's precessing. And Earth does the same thing, plus or minus about half a degree. Sometimes the tip is 23 degrees, sometimes it's 24. And back then, I believe it was closer to 24. And so if you go to Stonehenge today, none of the alignments work because the tilt of the Earth has changed. And so nothing lines up anymore. But on a computer simulation, it's real easy. You can not only build the structures as they were meant to be, not as they currently are, but you can also change the whole tip of the planet. So on the subject of building the way they were meant to be, of course, there's a little bit of guesswork because some of the stones are gone. But there are these repeated structures. You can figure out from the other ones what was intended with the missing ones. But some of the outlying stones are astronomical. You do have a little bit of guesswork. Usually you make them flush with the horizon. I'll try to point out the guesswork where it appears.
But another nice thing about it is you go to Stonehenge today, it's usually gated off. You can't get into the middle. So one, the alignments aren't even going to work because the Earth's tipped over. And two, you can't even stand in the center, except on special days. They're opening it up a lot more these days. But with the software, you can do it, no problem. You just stick yourself there. Well, I stuck the tilt of the Earth in, went looking for the alignments, and still one thing was missing. And it turns out, after much reading and thought, it's an atmosphere. The atmosphere actually changes the position of the sun and the moon on the horizon. If you look straight up, you're not looking through a lot of atmosphere. I had this figure up from before when we were talking about eclipses. The atmosphere is paper thin. If you're standing here on Earth and looking up, you're not looking through much atmosphere. But all this astronomy is done on the horizon, the rising and setting point. So you're looking kind of in this direction. And there you're looking through a lot of atmosphere. And atmosphere bends the light. It's kind of like when you're looking at a straw in a glass of water. As the light coming from the straw transitions from the high density water to the lower density air, you get refraction, a bending of the light. In the atmosphere, a long swath of atmosphere will do the same thing. It bends the path of the light just a little bit. If you've ever watched the sun set, the sun actually set about a minute beforehand. And the light is being bent up into your eye over the horizon. Kind of like this. The sun, instead of being over here, is here, and so the light's coming up, but the atmosphere bends it into your eye. And that changes the locations of the sun and the moon on the horizon, so you've got to build an atmosphere as well. So all that's in there. And I'm not going through all this to talk about how great my software is, but I just want to let you know it's not an easy thing to do, and it's all in there, so we can play now and feel relatively secure with the results that come out of it. Now, in that amount of time of talking, you can see how much the moon has moved. It's now behind this giant trilithon. Okay, before we do alignments, let me just give you a tour of the three phases. So you have different options. You can stand on the ground, you can sit on the ground, lie on the ground. You can also go up on the lintels. That's something cool you can do that you can't do nowadays. They won't let you climb up on the rocks if you go to Stonehenge. But in the simulation, you can do it. In fact, I found an alignment up there no one ever found before. There are only about like 20 alignments at Stonehenge. They're all well known. But I found one. It might actually be pretty significant. I'll save that for the end of the presentation. But let's hit other. We're going to go 50 feet up. We're going to get a bird's eye view. And the entry screen popped up on my monitor, so that's why you didn't see it. I just typed it in, 50 feet up. And location, there are many places that are good to stay in. The center of Stonehenge, which shifted during the different phases. These station stones, we'll come back to them. Right now we'll hit other, and I'll type in over here 500 feet out along the main axis, and we'll just turn around and look back. I'll just click on a stone here. Oops. Okay, so we're off the top of the screen, looking back 50 feet up, simulate, and so bird's eye view of Stonehenge Phase 3, which is the Stonehenge that's there today, just fully reconstructed, at least to the best of my knowledge. So you got the complete circle, you got these 5 archways in the middle called trilithons. The biggest one actually stands up well above the height of the circle. That has since fallen down. It fell down in 1904, if I recall. You see the outlying stones, these are going to be the astronomical marking stones, and there's some holes in the ground. Those holes are no longer there. They've been backfilled with time. They dug the holes and put nothing in them. No one knows why. And that's the actual Stonehenge horizon. You need that as well because when you can see the sun depends on how much of the hills it has to overcome, come above and be visible. So that's phase 3. Let's go back a phase. Just about 150 years earlier, before they brought in the giant sarsen stones, you just have the little stones. They're in a different configuration. These are called blue stones because they have a blue tint to them. They're rumored to have magical healing properties, and so people have been chipping away at them a lot in the past century. That's why most days you can't approach the stones anymore. But they're in a different configuration. We'll come back and look at this in a little bit. You can see the moon hanging up there. And let's go back to phase 1. Okay, here we are in phase 1. And this doesn't look anything like Stonehenge, but this is how it began around 3000 BC. There's a circle of holes called Aubrey holes, named after the guy who discovered them in the 18th century. We have 4 stones. 2 of them are marking due northeast, marking a cardinal point to the compass. These are these over here. And then we have these almost marking northeast, a little bit off. We'll come back to them in the sequence of posts. And the archaeologists can tell there were actually posts there. Now, one thing that's not simulated here, it was beyond my computing capabilities, is the henge, Stonehenge. Henge has taken on different meanings over the years. It literally means hanging stone, Stonehenge. So you go there and you see all these stones over your head. And those are the lintels. But over time, the word henge has also come to mean the earthen mound. The site is surrounded by a mound. It's been worn down tremendously with time. But I'll bring up a picture of it here. Bring the manual over. It's here. Okay. It's over here. Okay, so here's the henge. Now the ground there is hard white chalk. It was not an easy thing to dig. And when they first dug it, it must have been brilliant to look at, the gleaming white chalk. Over time, it got covered with dirt and grass and whatnot. It's two mounds. The inner mound is 6 feet high. And people are shorter back then, so you could not see over. You could not see the horizon, except in two locations. One is due south, and they understood the cardinal points of the compass, even back then, even thousands of years before this. At this very site, there's evidence in the ground of people digging holes in an east-west direction. So they're able to figure out, yeah, all the stars move around one point. That represents north, hence you have south, east, and west. So cardinal points of the compass are well understood by this point. The other opening's off the top of the image, and that's not due northeast, but close to northeast. And that will be the location that the sun comes up on the first day of summer. Now, these structures were actually quite common. They kept down livestock in here so they didn't wander away, gated up the entrances. But this one started having an astronomical application. And nowadays, it doesn't look like that at all. It's been worn down a lot with time. I'll bring the picture over. You just have this kind of little trough there, much smaller than a person. And so it's a very different sight nowadays. But you'll just have to imagine the henge, because I couldn't code that aspect of it. Okay. Let's end this simulation. So here we are at phase 1. I'm going to cancel that, and we're going to stand back on the ground. Now, you want to see the astronomical simulation, but before I do that, we're just going to review horizon astronomy. Main menu, Stonehenge astronomy, sun and moon astronomy. So this is what I was talking about at the beginning of class. This is the eastern horizon. Where the sun rises on the eastern horizon depends upon season. Here we are in summer, fall, winter. We hit a standstill or a solstice. Spring, and then another standstill or solstice. So the winter solstice, the southernmost, I don't know if I mentioned this before. I don't think I mentioned it yet in this class, so it's kind of interesting. The winter solstice is December 20th. Did I tell you about the origin of the Christmas holiday? Why it's December 25th? Have we talked about that? No, it's kind of interesting. So December 25th, the birth of Jesus. You ask biblical scholars, Jesus was born in the spring, probably April, I think, but not December. So why did the early Catholic Church pick December 25th as the date for Christmas? And what it is at that time, widespread, there's celebration of a pagan holiday that they're trying to supplant, and that's the first motion of the sun from the solstice position. Now, as the sun's rising on the horizon, moving farther and farther south, the days are getting shorter, particularly up there, much higher latitude, harsh conditions, and the rising point of the sun starting to move back towards the north is indication that spring is coming, and the days are getting longer and conditions will get easier, and something they celebrated. But the human eye can't see the motion for about 3 or 4 days. Sorry, I thought I was losing my mic there. For about 3 or 4 days. So the celebration occurred days later, around December 25th. And hence, that's why Christmas was selected for that day. Anyway, kind of interesting fact. But the swath across the horizon is quite large. It's about 80 degrees. So the rising point of the sun can change tremendously with season. Okay. Now the moon, let's review the moon, because the moon is actually trickier. The moon, as you can imagine, does the same thing, not over the course of a year, but over the course of a month, and this would be a sidereal month, 27 1/3 days, doing a full cycle on the horizon. But it's trickier because the Earth-Moon plane is tipped with respect to the Sun-Earth plane. And we got the regression of the line of nodes, the precession of the Earth-Moon system. And the way that manifests itself as horizon astronomy is the endpoints change with time. You got the moon here. Sometimes it does 80 degrees of the horizon, but sometimes it can do as much as 100 degrees on the horizon. So here's a 100-degree span of the horizon. And so the endpoints actually change with time, slowly, over approximately a Saros cycle. This isn't tied to the phase cycle of the moon, it's tied to the sidereal cycle of the moon. So it's not 18 years and 11 1/3 days, it's about 18 and 2/3 years. But the endpoints wobble over this kind of generational time scale. So if they mark it and they come back the next year, they realize that the marking has changed. And again, the moon is not useful as a calendar. They just got interested. They started marking lunar alignments. They come back year after year, and the endpoints are changing. And after about a generation or so, they figured out there's this additional cycle due to the two planes, one precessing with respect to the other. And so you'll see that here. And then all they have to do is mark it. We talked about markers, but let me just show you different types of markers. So here it is all marked up. These are simple single stone markers, winter solstice. And for it to work, it has to be a good distance away. If it's really close to you, if you wobble your head, the alignment doesn't work. So that kind of dictates the minimum size of these sites. And here's the lunar cycle, and it's marked. And then the endpoints. Again, it doesn't move like this, but if you take the extreme point each month and plot it, you see over 18 2/3 years, the endpoint shifts. And finally, you can have different types of markers. You can have a single marker. You can have framing. You can have secondary, where the first one marks with the horizon and then the other ones follow it. And a final one, boxing, which is kind of nifty. They can be made of stone. They can be made of post. And also you can have different amounts of illumination. That's half disk, but you can have zero disk, which you just get the first glimmer of light, or you can have full disk. All sorts of different ways you can have alignments. Okay, so that's enough prep. Let's look at some alignment. Go to Stonehenge 1 center. And so we want to look at the summer solstice sunrise. So let's get back on the ground. And here's date, so year, month, day, hour, minute, second. 30, 99, negative 39, that's 3100 BC, because there's no year 0. I didn't program that in, so that's really 3100 BC. And so we just need to know the time of summer solstice sunrise, 3100 BC to the second. So who has that? Okay. I have it. So the program will find it for you. Changed it. Now you say 3:30 a.m. That's crazy, but no daylight savings time. This is much farther north, and so the days are longer. It's actually correct. So we'll look towards the sun, and we'll simulate. And so here you are, 3100 BC, and it's dark. The sun's coming up. Let's zoom in. Oh, there it is. And we can also change the rate at which time flows. So that's kind of convenient. So we're going to look at a bunch of sunrises and sunsets, and we don't have to wait for them to occur. So this alignment is kind of interesting. And the ones we talked about before is you just stick a stone there to mark it. This one is what we call a half-disk framing alignment. See, it's halfway between two stones, and half the disk of the sun was above. So half-disk framing alignment. And then it goes on. That's the summer solstice sunrise alignment marked 3,100 years ago. That's kind of cool. Now these stones here, they're kind of interesting. They frame due northeast. There's no alignment there. It's framing a cardinal point of the compass, northeast. It's almost as if they say, okay, the alignment, the first day of summer is here, kind of northeast. It's not quite perfect, and they frame what they deem to be perfect as well. But who knows what the rationale was? There's no written record. Now there's one more alignment in phase 1. It's a lunar alignment. As I said last time, these indicate that they're going above and beyond just making a simple calendar, because the lunar cycle doesn't divide the year into an integer number of months, so it's not useful as a calendar. The fact that they studied it is very interesting. So let's take a look at that. Moon, maximum northernmost moonrise next. I'll stand at the center of Stonehenge 1. Look at the moon.
You can see it's going right over that post. So kind of a traditional alignment. Actually, let's change it out here more permanently. We'll make things go 15 times normal speed, 20-degree field of view. And so you can see the clip of it there. Now, I think it would really suck if you wait 18 2/3 years and it's a new moon and you can't see anything. So I can add the lunar limb and outline of the moon there. So we have first glimmer over that post. Now, of course, the post is no longer there. I have to guess the height. But for all the missing stones, you pretty much make it flush with the horizon. And that's Stonehenge's actual horizon, where they've measured in modern days, and I've added a pixel because there used to be trees there. And then the other ones I just have to guess. And since it's posts, that indicates, if it was kind of short and low to the horizon, they would have used stone. A post means they needed something taller than they could do with stone back then. And it's also a temporary thing. You wouldn't leave it out there, it rot. So you take it out there once every 18 2/3 years, set this up. So I just guessed that the moon just kind of rides on top of the posts. You can imagine it just continues on its way up there. But that's kind of my guess. We know that there were posts in this pattern. You might also notice they're evenly spaced. Stonehenge is laid out on a grid. They have their own yardstick, a little bit longer than our yardstick. We call it a rod, but who knows what they called it. And Stonehenge is laid out on a grid. It's also an angular grid. They have certain angles they like to repeat structures on, and also certain distances that they like to place stones measured in rods or half rods. It's really kind of interesting. They laid the thing out very expertly given the technology of the time. Okay, that's phase one. Is this interesting? Should I go on? Okay, good. Phase two. So this happens many hundreds of years later. Totally different culture moved in. They saw what was there before, decided to add to it, and they went quite some distance. They added all these small stones in this structure in the center and a bunch more stones out here in the outskirts. They went all the way to Wales to get them, which is hundreds of miles away. I'll bring up a map. So the stones, geologically, we can figure out where they came from. It had to be from this location in Wales over here. And each one of those is 7 tons. The big ones in phase 3 are 50 tons. These are 7 tons. And so the most likely way that you're going to move them over long distances is by water. So you float them down, you build rafts, and you float them down the river in this way, and there's another river. And you can get within 25 miles of Stonehenge. Then you have to haul them over hills like this. And that really sucks. So most people think they probably went the long way around. There's another river that gets you within 7 miles, and then it's a straight shot. And people used to think that they used log rollers, but you could try that. You could put a 7-ton or a 50-ton piece of rock on logs. It just kind of crushes the logs. Or at least they can't move. The friction is too strong. You can't move them over the logs. But this was probably done in winter, because during the summer, in the spring and the fall, they're working the crops and the harvest and all that. So probably the winter, that's when you have the free time. So the idea is they dragged them over the snow and ice. And a couple years ago, an astronomy professor in Britain tested this. He took his intro Astro 101 course, said, okay, everyone outside, and lashed them up to a 50-ton boulder. And the calculation said it would take like 1,000 big burly people. If you work the land, you're big and burly. If you sit in front of a computer, you look like me. And so he lashed the students, which most of them look like me. Being British, no, I retract that. To a boulder, and he only had like 350. He didn't have 1,000. It was one of the 50-ton ones from phase 3, and they could do it. So you can actually move these things. You don't have to say, well, it must be aliens or all that crazy stuff that you hear about Stonehenge. It's all very doable. There's a great video on YouTube. I don't have time to find it or show it. There's a guy who built his own Stonehenge somewhere in America by himself. Using just the technology of the time with pivots and seesaws and things, and he can move these things around and dance them and place them single-handedly, 50 tons. So this stuff can be done. But, I mean, there are all sorts of stories, myths. Merlin brought these stones from Ireland is one of the myths. And you can see where that might have come from reality, because Wales is as close to Ireland as you're going to get without crossing the water. So there's probably some truth in the myths. Okay. This is the most astronomical phase by far. There's like a dozen, I think about 16 alignments here. In the inner area, alignments always occur with the faraway stones. If you have a stone really close, like I'm doing the eye thing, open one eye. Did we do this last time? No, okay, go ahead, stick your finger in front of your eye. This is called parallax. We'll see it again in a couple lessons. Close one eye and look at the part that your finger's covering up. Imagine the sun rising there. Now switch the other eye. It doesn't work anymore. But if you put your finger farther away, the shift is less. And then, cut your hand off and put it farther away, the shift is less. So if you put your marker stone farther and farther away, it becomes more and more accurate. But if it's nearby, just bobbing your head will ruin the alignment. And so, for that reason, the nearby stones are probably not alignment markers, but these outline ones are. Let's look at the nearby ones first. They arranged them in this kind of semicircle structure. A lot of experts say, why did they never complete it? But we don't know that. This might have been completed. It might have been on purpose. If you think about it, it took a lot of people to haul all this stuff from Wales. And to set up this structure, to look at the summer solstice sunrise, winter solstice sunset, and all these different things. But only one person can stand at that perfect location where the alignment works. And that's going to be like the most important person. Or maybe 3 people can crowd in there. It'll be your political leaders, your religious leaders, the power structure. But they're doing something important. They're going to want everyone to see them doing something important. So I imagine they left it open on purpose. The poor saps who had to haul all this stuff from Wales would sit off on the left and watch them do the important religious ceremonies tied to these alignments that they've marked. That's just my hypothesis. Okay, let's look at some of these alignments. We won't do all of them, but I'll hit the highlights. Summer solstice sunrise next. We'll stand at the Stonehenge 2 center. Look towards the sun. Again, it's going to be off the top of the screen. Now, one of the stones here is gone now. Actually, nowadays, all the stones here are pretty much gone except this one stone. Did I talk about it last time? I'm sorry, I just did this for the other Astro 101 class, and I forget what I've told who. So just a little aside here, I'll show you the heel stone. That's the one stone that's still left. And this is what actually got everyone thinking about astronomy at Stonehenge. If you go to Stonehenge today, there is one alignment that works. The sun rises over the heel stone on the first day of summer. Never intended. As you just saw, there were 2 heel stones. Heel for Helios, sun. There were 2 of them, the sun came up in between. But since then, the Earth has tipped over. There's nothing else out there to look at, so your eyes are naturally drawn to it, and someone tipped it over this way, so it's flush with the horizon. There's a triple coincidence. The most important alignment works nowadays, but not as intended. It got everyone thinking about astronomy at Stonehenge. Anyway, that was an aside. In phase 2, they've added, hide those spots, 2 more stones. One is a first glimmer of light, and the other is half disk, just a little bit off to the right. So there you see first glimmer. We'll let it tick once or twice. It used to be that the computers were really slow, so I didn't refresh the screen any faster than this. I need to update that. We could have continuous motion. So first glimmer, half disk. They're very precise in their alignments. And you can see it's also framed in the foreground. They added extra blue stones along this axis, indicating its importance. Now in phase 1, we had maximum northernmost moonrise. Here's minimum northernmost moonrise. Moon, minimum moonrise next. So we'll stand at the center, look at the moon. So you can see the minimum is going to work there as well. There's the moon. Let it go 1 tick. Tick. Now if you look over here, you actually have a mini version of the same structure. Remember, this has a big mound around it, the henge. But actually this one here and this one here have mini henges around them, suggesting they're important. We call these 4 stones here, 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 and here the station stones. North, south, east, and west. North and south appear to be important places to stand. So they have their own hinges. So if you stand here and look in this direction, that's summer solstice sunrise. Here's your maximum northernmost moonrise. Here's your minimum northernmost moonrise. It's a little mini version off to the side. If you stand here and look back, that's winter solstice sunset. It's opposite of summer solstice sunrise. Same thing over here. Summer solstice sunrise, winter solstice sunset. I'll show you the winter solstice sunset. So we'll stand at the northern station stone. Event, sun, winter, sunset. Next, time change. Look at the sun. There, and it will be setting over that stone. There's an equinox alignment, also from the northern station stone. So we'll stand at the northern stone, event, sun, equinox, sunrise next. And we'll look towards sun. And although it looks to be a little bit to the left there, it's coming up at a glancing angle. So I think you have half disk over this stone. Now, what's interesting about this stone, if you're standing at Stonehenge center, see that one on the left is the heel stone, and these are the two stones they added for summer solstice sunrise. So this stone right here is serving two purposes. Look at this way, it's summer solstice sunrise. Look at from over here, it's equinox. And a lot of the stones here serve multiple purposes. End the simulation. And so, for summer solstice sunrise, they could have put those stones anywhere on this line. They chose to put this one here so it could also be an equinox, and then this one's evenly spaced a certain number of rods away from both of them. So they like even spacing as well. Let's see, there's winter, oh, let's forget this one. Let's stand so winter solstice sunrise next. Oh yeah, so right there, that was the maximum northernmost moonrise from here. It's also winter solstice sunrise. So clearly this is not random. And you can run the odds statistically. Just looking at the outline stones, what are the odds that they all hit astronomical alignments from the sun and moon set? And some of them multiple, some of them up to 3, I believe. 0. No chance that it's random. This was intended. You can prove it statistically. One last thing I'll show, if I can remember it. The station stone is very interesting. We saw solar ones run up and down. There are lunar ones that run across. There's only one latitude on the whole planet where these will form a perfect box, and it's the latitude of Stonehenge, which makes you think that they might have chosen the site for this. But then you think, well, it was the previous culture that chose the site. Did they have that in mind and didn't build it? So that's kind of a subject of debate. This is moon, I think it's moon set next. And we'll stand at the southern stone. Look at the moon. Yeah, I got it. And so as it goes down, it will hit that stone. Now that one is lower than the horizon because its primary purpose is winter solstice sunset, looked at this way, but it's also, since it's the corner of this box, it serves two purposes. And that works from this stone to this one as well. Okay, so point there is phase 2 is very astronomically related. They really got into marking these things. Questions about phase 2? Okay, we'll jump into phase 3. Phase 3, that's when they add in the big sarsens. And you can see most of the additions, it's in the interior region. We already said that if stones are close to you, they're not good at marking alignments. So these really aren't good at alignments. There are a few extra stones added out here in the outskirts. These clearly, it's a framing alignment for the summer solstice sunrise, so we'll look at that one last time, just because that's the most important alignment anywhere. Summer solstice sunrise next. We stand at phase 3 center, which they shifted the monument a little bit. So here you go. First glimmer, half disc, framed by these two stones. This one's still there. It's tipped over. They call it the slaughter stone, but that wasn't the purpose. This was the purpose. Framed by the sarsens and the blue stones, which have been rearranged into a circle. So this thing is majorly framed. Clearly important. Now, everything else, except for a special alignment that I'll show you in just a little bit, that I discovered with the software that no one knows about except you and all my other Astro 101 classes over the years. Let's just, before we do that final alignment, there is astronomy, although you can't have alignments this close proximity, there is astronomy there, a great deal of it. Two different ways. You have symbolic alignments and you have numerology. Show manual, main menu, architecture. So here's a diagram of the inner part with the lintels, the crossbeams are removed. And you have these 5 archways, the biggest one on the main axis. Turns out if you stand at the base of each of these, one of the primary alignments goes through a hole in the sarsen circle. Now, what are the odds of this? It's borderline. You can't say with statistical confidence this was intentional. It could be random, unlike the outline stones where you can say with statistical confidence that it's intended. But here it's kind of borderline, so this might have been the intention. You can imagine them having ceremonies under each of these 5 trilithons for certain things, and with this some of them multiple ones, and the big one being summer solstice on the main axis. So there are symbolic alignments. One thing that lends credibility to this, I think it's this one. If you go there, it doesn't actually work. The stone would be in the way, because they're not perfect rectangles like I've depicted here. They're bumpy and lumpy. But someone in the past took a mallet right at eye height to open it up that sight line so this alignment would actually work. Maybe. Okay, numerology. So 2 numbers are very important in the phase 3 architecture, and also phase 1. 29.5, which is what? The month, the sidereal or the synodic? Synodic, the phase cycle, which is the easiest thing to see. And then this number, 18 2/3 years, which is the oscillation of the endpoints on the horizon, which was a hard 1 number. So it took them generations to find it. Well, let's start counting things. They have the blue stones arranged here in a horseshoe. There are 19 of those. That's pretty close to 18 2/3. These blue stones are a circle. There are 59 of those. That's twice 29.5. Number of lintels, 30. Number of uprights, 30. And although I don't depict it, the southernmost one is half as wide. So it's like they're really meaning 29.5. Then they dug these holes that were never used. Who knows what they were planning for? Maybe they're going to put stuff into it. It's a very interesting expanding spiral where the radius here is like 14 rods and the radius here is 15, 16, and 17. It's laid out on their grid. They never used them. They're backfilled with time. They've only been determined from sensing sonar-like devices. But there are 59 of those, again, twice 29.5. And if we go back to phase 1 and count the Aubrey circles, there are 56 of those, which is 3 times 18 2/3. So all repeated structures above 5, the 5 trilithons, appear to have these 2 astronomical numbers built into it. You can't make a statistical argument saying whether that was random or intended, but it seems intended to me. Okay, 2 last things I'll show you. One is eclipses at Stonehenge, and I bring this up because of this circle here. This is one of the things you might find on the internet that I just don't think is true. But a little history here. How was all this discovered? I didn't discover all this. I just coded it up. I discovered one thing, and I'll show you that. But back in the 60s, there's this astronomer, Gerald Hawkins, American astronomer, who showed up at the surveying crew for 3 days, surveyed everything, and left. And the British archaeologists who had been studying the site for hundreds of years just laughed at him. What's this American astronomer think he's going to do? He went back, put all the numbers in this newfangled contraption called a computer, and statistically showed that the site was astronomical. Which really pissed off the archaeologists because they never even guessed that. And so they fought the astronomers for decades. They're like, no archaeological sites are astronomical, and they really hated it. Statistically, we can prove it. This site is indeed very astronomical. Not saying that's the primary purpose. It's probably a political, religious center, but astronomy is built into it very heavily. He was right about all that. One thing I think he was wrong about was the Aubrey circle. 56 of them. He said that this was an eclipse predicting computer. And I'll bring up the image, and it might look familiar. And I bring it up because we just talked about line of nodes. So it is kind of relevant. So he argued that if you put 4 stones in these holes, one representing the sun, one representing the moon, and 2 representing the nodes, you draw a line between those 2 node stones. That's the line of nodes. If you move the node stones at a certain rate, the sun at a certain rate, the moon at a certain rate, corresponding to the rates they actually move around in the sky as we understand today. When the sunstone, the moonstone, and the node stone all land in the same hole, you have a pretty good chance of an eclipse that day. But I don't think it's accurate. I don't think it's right for a couple of reasons. One, this computer suffers from tremendous round-off error. You quickly build up half a hole, 3/4 of a hole, and it's in the wrong hole. You pretty much have to recalibrate it monthly for it to be accurate. Secondly, the archaeologists who hated the astronomical hypothesis at the time, they accept it like now, took great pleasure in pointing out that those holes are full of human formations. There are no stones being moved from hole to hole. They're full of people, at least on the main axis and the southern entrance. Those were like the places to be buried. So it falls apart. But I bring it up because it's relevant to what we're talking about. And since I have the sun and moon equations in here so well, We can actually look at an eclipse over Stonehenge, so might as well try that. That might be fun. Event, solar eclipse. We'll take a total. Next, and we'll look at the sun. Okay, and we'll make this go kind of fast. Eclipses take a while. So we'll go 75 times normal speed. I got the lunar lens still on. Let me take that out. So you can see the moon's right there up against the sun. Move it. I'll bring up a magnifier where we can look at the sun or the moon. Doesn't matter. And so this is what eclipse over Stonehenge. I think the year is 280 BC. So well after it fell out of use. If you were there, this is what it would have looked like. Except I kind of cheat with the colors. I'm making the sky darker than it would appear to the eye. As I said, with partials, you don't even realize it. I'm exaggerating it a little bit for effect. I don't know why one disappeared and the other. I guess it's such a small sliver. Oh no, I don't know, where'd my sun go? Oh, there it is. Oh yeah, just a few pixels on that screen. Okay, last thing I'll show you is the alignment I found. So the archaeologists think there was a stairwell on the southern side, that upright that's half as wide. There's some evidence that there is possibly a stairwell to get up on the lintels. Now, you ask permission to go up on the lintels now, they just laugh at you. No one's allowed up there. The circle's not complete anymore, so it's not as structurally sound as it was when it was built. Very stable structure. It's not a surprise it lasted so many thousands of years. Well, but in the computer simulation, you can come up here. So I'd walk around and look around. And one day I got tired and sat down here on the main axis. So let's sit on the lintels, look in this direction. And this, I'm beginning to think, is the most important alignment in Stonehenge. Maybe even more important than the summer solstice sunrise. But don't quote me on that. I should go back to the beginning of phase 3. I can do that. And then winter solstice. Sunset. Next. And we'll slow it down 10 times normal speed. Let's start with a fisheye view. So you know what it's like to sit on the lintels. It'd be kind of cool to sit up there. So that's a fisheye lens, so you can see 180 degrees. End it. And we'll come back to a smaller field of view, let's say 25. So sitting there, you're looking right across the Great Trilithon. People always ask, why is the Great Trilithon so much taller than the others? Well, if you're sitting on the lintels and your eye height is just right, it's a perfect box. I don't quite have it right here. If I fiddle with it, I think what I'll get is the eye height of the architect of Stonehenge. And he probably designed it to be a perfect box for him sitting there, or her. No way to know it. And anyway, last glimmer of the shortest day of the year, right there, sitting on the lintels. So that's a pretty cool thing, I think. Okay, so that's Stonehenge. Questions about that? You like that? Okay, good. Oh, class is over. Oh. It's okay, ask your question, Will.